Welcome to the video on Boolean Algebra, a mathematical logic system. This system is a core part of digital electronics, used primarily to simplify digital circuits and expressions. Boolean algebra is a mathematical logic system using only binary values, 0 and 1. It is essential for designing and analyzing digital hardware. One of its key benefits is simplifying complicated equations into small, efficient expressions. Boolean algebra is important for several reasons. It reduces circuit complexity, which saves hardware, leading to smaller boards and lower costs. It also improves performance by allowing shorter logic paths, and it is the mathematical foundation for computer processing units. Boolean variables are represented by capital letters and are strictly binary. They can only be 0 or 1. These variables are combined using logic operations to create complex decision-making circuits, where any value not equal to 0 is 1, and vice versa. Boolean algebra relies on three fundamental logical operations: OR, AND NOT. OR is logical addition, represented by plus. AND is logical multiplication, represented by prechen. NOT is logical inversion, represented by a prime symbol or a bar over the variable. The identity law states that a term ORED with 0 or ANDED with 1 always equals the original term. This means A plus 0 equals A and A quet 1 equals A. These rules are confirmed by the truth tables shown. The null law, also known as the dominance law, states that a term ORED with 1 is always 1, and a term ANDED with 0 is always 0. The rules are A plus 1 equals 1 and A ang 0 equals 0, as demonstrated by the truth tables. The complement law states that a term ORED with its complement equals 1, and a term ANDED with its complement equals 0. The rules are A plus A equals 1 and A fit A equals 0. The truth tables illustrate these complementary outcomes. The idempotent law means that a term ORED with itself is equal to itself, and a term ANDED with itself is equal to itself. The rules are A plus A equals A, and A capital A equals A. This is supported by the corresponding truth table. The commutative law dictates that the order of variables does not matter when they are ORED or ANDED together. You can safely swap input positions without changing the final output, meaning A plus B equals B plus A, and A plus B equals B plus A. The associative law applies when ORing or ANDing three or more variables. The way they are grouped does not affect the outcome. Brackets can be shifted, so A plus B plus C equals A plus B plus C, and A captivate. Here is a simplification example. Starting with A plus A quef B, we factor out A to get A quef 1 plus B. Then, applying the null law, 1 plus B equals 1, resulting in A quef 1. Finally, using the identity law, the simplified result is A. For a second example, start with A quus A plus B. Distributing A gives A quus A plus A quus B. Apply the idempotent law, A quus A equals A, resulting in A plus A quus B. This is the same expression as example 1, simplifying to A. Boolean algebra is widely applied in circuit simplification, reducing the number of logic gates needed. It is critical in digital logic design, used for components like multiplexers and decoders. It also forms the logic for the arithmetic logic unit inside computer processors. In summary, Boolean algebra simplifies circuits, transforming massive expressions into efficient logic designs. It uses logical rules like the null, identity, and idempotent laws to solve equations step by step. It serves as the digital core, the foundational theory for digital electronic systems. Thank you for watching this video on Boolean algebra. We hope you keep learning and keep growing. Feel free to like, share, and subscribe for more content.